Hello and welcome to probably one of the most exciting lessons in geometry or vectors, the dot product. The dot product, as the name says it, it's a product or the multiplication that we perform amongst two or more vectors. It's a form of multiplication, I would say, and it is so easy to learn and understand. Say, for example, if we have two vectors given in standard form, here is vector A with coordinates xa, ya, and some vector B with coordinates xb, yb. Fancy, isn't it? Then we're going to say that the dot product of A dot B, that's exactly how we read it, would be equal to xa, ya dot xb, yb. Nothing fancy, right? Then we'll perform the multiplication. I want you to guess. So I'll pause for a second and guess how would you multiply these two vectors. So I will multiply xa by xb. So I told you it's easy. And for y, I will multiply ya with yb. And voila, there we go. Say, for example, that A actually is some real vector. It has the coordinates 2 and 3. So B is some real vector again, and the coordinates are -7 and 2. So therefore, we're going to say that A dot B equals 2, 3 dot -7, 2. So that must be then 2 times -7, which is -14, and for the y coordinate, we have 3 times 2, which is 6. Isn't this super easy? Okay, so now we're going to take a look at various forms of expressing the dot product, and we're going to see the practical use of dot product in everyday life. Now, a dot product is also known by the name scalar product. And the reason why we call it a scalar product is because the answer will be a number or a scalar. So how does that happen? What we got in here were coordinates. So remember that the vectors that we worked with here were in component form, but most of the time we work with vectors in standard form. And if vector A, the same vector A here, were to be expressed in standard form, it would be 2i plus 3j. And vector B, that same vector B we have in the previous example, would be -7i and then plus 2j. So when we multiply or dot product these two vectors, A dot B would equal, again, we're multiplying 2i by -7i. That's -14i, that will be squared. And then plus 3j times 2j, which is 6j, which will be squared. So I is a unit vector, so the value of I is 1, and so is the value of j. So -14 plus 6 equals -8. So we'll say that the dot product A dot B equals -8. Mind-blowing, isn't it? And now we're thinking, okay, but how do I use this? So what am I studying it for? There are a lot of connections that this type of multiplication has with very famous geometry formulas that were discovered millions of years ago, probably. And we are going to take a look at these connections. But before I do that, I think it's time for us to look at the definition of dot product. Now, the dot product is a form of vector multiplication, as we said, and is denoted by this little dot in the middle that stands for the multiplication, and that's where the name dot product comes from. And there is a formula we can use, actually, to find the dot product of two vectors. So u dot v, here we have the vector form. That's what we were doing here. So we use the vector form to find the dot product. It can also be found by multiplying the magnitude of u with the magnitude of v, and then the cosine of the angle made between the vectors u and v. And you're probably wondering, okay, so how is this going to work? Is it true that this left side, which was found by using vectors, could equal this right side where I see just magnitudes and some angle in between? So with this in mind, we're going to go back to our examples. Now remember, we worked with vectors A and B, and we'll highlight them because they're becoming so important now. So here is vector A, and here is vector B. Now, we already know their standard form, and we found the dot product of the two vectors in vector form, in standard form, and we got this number, -8. So this would be A dot B, or in other words, remember the formula we just talked about is A dot B equals magnitude of A, magnitude of B, and then cosine of the angle made between these two vectors. So now I'm going to use the same vectors, A and B, and I will find their dot product using this part of the equation or the formula. So my mission now is to find magnitude of A times magnitude of B times cosine of the angle between them. And I'm thinking, how do I find the magnitude of A? Well, I have the vector A. Can I find the magnitude? So I'm going to say, yeah, the magnitude of A equals the square root of 2 squared plus 3 squared, and that's the square root of 13. The magnitude of B, on the other hand, equals the square root of, here is the x, here is the y, so -7 squared plus 2 squared, and that would be 49 plus 4, which is 53, the square root of 53. Now I have to think of what angle do these vectors make with one another. How can I find the angle between them? So in order to find the angle between two vectors, I'm going to show you, or I'm going to draw a diagram here just to create or to give you an idea of what's going to look like and why we're doing what we're doing. So imagine that vector 2i plus 3j, so vector A, would be 2 and 3, right? So it would be this vector here. So this will make a certain angle with the x-axis, but that's just vector A, right? So vector B, on the other hand, is -7i, so we're going 1, 2, 3, 4, 5, 6, 7, and then plus 2j, so it will be somewhere in here. And now we're thinking, here is vector B, here is vector A. How do I know what angle they make with one another? And now we're thinking, okay, if I only knew the angle that vector A makes with the positive x-axis and the angle that vector B makes with the positive x-axis, then we would say that the angle between these two vectors will be, I'm going to call this angle alpha, and this one angle beta. And this will be the angle theta, the angle between vectors. So we'll say angle theta then must be beta minus alpha. Do we know how to find angles alpha and beta though? So remember that to find the angles any position vector makes with the positive x-axis, we use the tan ratio. So we're going to start off with angle alpha. So we'll say alpha equals inverse tan of, and now we're going to use the y and x coordinates, so 3/2. So that will give the angle alpha equal to, let me calculate it, so 3/2. So I got 56.3 degrees. 1 decimal place would be enough. And now, in the same way, I'll find angle beta. So beta equals inverse tan, and obviously we have to use the x and the y of angle B, of vector B, sorry. So this would be y, and this is x, 2/-7. So angle beta then will be inverse tan, 2/-7. That's negative 15.9. That's what the calculator will give you, or about negative 16 degrees. And that is because it will allow us, or it will give us the smallest angle that is made with one of the axes, right? So, which means that we're probably given this angle right here, 16, which makes the angle beta equal to 180 minus 16, because we know the location of the angle beta. So 180 minus 16 is 164 degrees. So we'll say that angle theta then must equal 164 minus 56.3. And that is about 107.7 degrees. That's angle theta. So now we're going to say we're ready to find the value of A times B times cos theta, because we know A, we know B, and we have finally figured out what theta equals, and theta equals 107.7. Let's check and see if we get the same answer. So we'll say that we have A times B times cos theta equals root 13, root 53, cosine of 107.7 degrees. And for this, I'm just going to use the calculator. And I encourage you to do the same thing on your own. So we have root 13 times 53 times cosine of 107. So I got negative 7.98. And if I had to round this, it would be negative 8. And you probably understand the reason why we didn't get exactly negative 8, as we did with multiplication in standard form. It's because of a lot of rounding that happened in here as we were trying to calculate it. So at least we can now see the connection between the multiplication of two vectors, the dot product in standard form, where you just work with the coordinates, and finding the dot product by using the magnitude of each vector and the cosine of the angle between them. So I hope that this has established some trust in what this formula means, and some trust in the fact that this formula does work and it does make sense. Now, what is the use of using the dot product anyways? Because that sounded a little bit complicated. Easy at first maybe, but it got a little bit heavier maybe as we were trying to, make or find the connections between the two sides. Well, the main use of dot product is finding the angle between two vectors. It's very useful. It's a quicker way of finding angles between vectors. But again, we are going to see together in the future lessons how the dot product can help us discover, or should I say rediscover, some of the most famous geometry and the most ancient geometry formulas and theorems that were discovered many, many, many years ago. Now, I'm going to discuss with you the sign of the dot product. As you see in our random example here, which by the way I just made up these numbers, we got a negative answer. So it seems that dot product can be a negative number. So why did we get a negative number here? Remember, we multiplied an absolute value with another absolute value and then cosine of an angle. And we got a negative. So the negative came from the fact that the cosine was negative. And the reason why the cosine was negative is because the angle was greater than 90. So we'll say that for angles between 0 and 90, the dot product will stay positive. Equal to 90, dot product will be 0. Between 90 and 180, dot product is negative. So we have a dot product app that I would like to share with you. And let's take a look at it together, actually. So U1A4, here we go. Here we are. Sorry, I didn't want to do this, but I do want to open it. Sorry. Okay, it's okay. Here we go. Dot product. So what you see here is two vectors, vectors u and v. And the angle made between these two vectors is 69.6 degrees for now. So on the side in here, you have also the dot product, which is indicated. So see here we have the points A, B, and C, all right? So this is vector u, this is vector v, and we have the dot product here, u times v. So I wanted to focus on this little rectangle that I'm highlighting here in gray on the left side of the screen. And I'm going to change the value of one of the vectors. So I'm trying to keep the direction the same in here, but I'm just changing the magnitude. So as you can see, the magnitude is changing. Now, as this vector is moving on the other side, notice how the dot product is negative. So negative 3.2, 3.5. That's because the angle between vectors u and v now is measured this way around, right? So it is bigger than 90, and that's why you get a negative dot product. In a similar way, we can play around with vector v. So when vectors u and v make an angle less than 90, the dot product will stay positive. So you see 0.5, 1.6, 2.3, and so on. And when you move it on the other side, when the angle is bigger, then the dot product will be negative and negative still, and then it becomes positive. So some of the properties of dot product are u, vectors u and v are perpendicular if the dot product is 0, and that's understandable because if cosine theta equals 0, it means that angle theta must be 90 degrees and vice versa. Now, if you have a vector u multiplying itself, the angle made between them would be 0. So that means that would be magnitude of u squared times 1. So that would be simply magnitude of u squared. Dot product satisfies the associative property with the scalar, so you can multiply in a scalar. And distributive property as well, so vector u dot v plus w would be the sum of each dot product. And commutative property, it doesn't matter in which order we dot product two vectors. As you can see, it's a scalar. It doesn't matter which number goes first, the vector v or vector u, you still get the same answer. Now remember that two vectors that are perpendicular will have a product, dot product 0. So I and j are perpendicular, dot product 0. J and j are the same, dot product 1. Now, if you are in 3D, I and k would be 0, I and I would be 1. So that is because the vectors are perpendicular. Same thing in here, k and j is 0, and k would be equal to 1. So this is in a nutshell what dot product is about, and I would really love to actually prove the cosine law using the dot product. It's a very interesting proof, but I'll do this in the next video. And thank you very much for watching, and I hope that you are really enjoying these lessons and you're really enjoying learning geometry. Bye for now.